Hi, I am Varun Joshi and welcome to day 24 of our Certified Kubernetes Administrator 2025 course. In today's session, we are diving into Docker volumes, the essential foundation for understanding how storage works in containerized environments, not only in Docker, but how it will look like when we move on to Kubernetes. What you see on screen is a Docker host. That Docker host is running 3 containers. Here is an image, and this image was created using this Docker file. The Docker file you see here is the same that we used in day 3 of our course. If you have any questions pertaining to this Docker file, I would request you to go and watch day 3's lecture. The image that has been created using this Docker file is of 50 megabytes. 50 megabytes is used for simplicity. The image that this Docker file will create will be of more size. We know that a Docker file can consist of multiple instructions, and these instructions can be bifurcated into 2 categories. First one is instructions that create layers, and another instructions that do not create layers. The instructions that create layers are from, run, copy, and add, and non-layer creating instructions can be seen here. But what are layers and why are we calling these layer creating instructions? So what happens is any instruction that generate data or modify the file system in any way are called layer creating instructions. If you look at from, then from uses a base image, and that base image uses some sort of storage. Hence, from is a layer creating instruction. If I look at work dir just specifies which one will be the working directory in the container. Hence, this does not take any storage. This helps the image in some way, but is not directly impacting the file system. So non-layer creating instructions are like metadata to the image. They do not perform a storage intensive task, any task that will generate data, but what they do is they help your containers either in build time or at runtime. Then you see add. Since add is used to copy data from your, let's say, Docker host to your image, hence add also generates data. Run, you use it to install packages in your image, hence run also generates data. Then expose and cmd are non-layer creating instructions. Now what I also understand from this image is more task my layer creating instructions will do, the larger the size of my image will be. If I am installing multiple packages in the run instruction, then accordingly my image size will be larger. If I am copying data from my Docker host to my image, which is of large size, then also my image will be of large size. Hence, it is recommended that you distribute these commands into separate sections. For example, there could be a stage where you are doing the build, and there could be a stage where you are defining your runtime instructions. So what you are essentially doing is you are using multiple stages in your Docker file, and few tasks that are only necessary for building your software are performed in a build stage, and then the things that are required to run your application, which are a mandate for your application, are available in the runtime stage of your Docker file. And I'm just using 2 stages as an example here, but you can have multiple stages. And if you have such kind of approach, what happens in the end is your image size is reduced, which is what we all want. The mechanism that I am discussing right now is called Docker multi-stage builds. If you have any confusions pertaining to this concept, then you can look at day 5 and understand this. But Varun, this is fine, but why are we discussing layers? So when you create an image consists of read-only layers. And why I am calling this a read-only layer? Because if you see, if this image is here, this image is shared between all these three containers, and any of these containers cannot modify this image. Hence, we are calling these layers as read-only layers. So what I mean by this is, if I talk about the total storage consumed by this Docker host at this moment, then we will only say that only 50 MB is consumed by Docker, because these three containers that are running are not using any additional data. They are just sharing this image, and since the image is read-only, they cannot modify this image directly, but they can write new data. And when these containers write new data, we call that a writable layer. So for example, if this container 1 modifies a certain section of this image, then it will either modify some data or generate new data. And those changes, that delta, is the writable layer. So when you run a container, you get a read-only layer, and that read-only layer is the image, and then whatever you write on top of it becomes the write layer. Whatever modifications you do, they become the write layer. If I scroll down, you see that now these three containers have started generating some data. If you see, this container has generated 4 megabytes of data, this one 10, and this one 6. This is understandable. So I also want to show you these layers in the terminal. So I am in day 3's directory, although we are sitting at day 24, because I want to demonstrate creating an image, and then we'll see the layers in that image. So here is my Docker file, and this is the same Docker file that you saw in the screen a few moments ago in this diagram. Now let's do one thing. I'll write docker build -p. I will name this my image, and then I'll add a dot, which signifies that the context is the current working directory. I'll press enter, and it has started building my image. Now once my image is built, I'll run docker image ls, and I can see that my image exists here, and then I will run docker history my image. If I press enter, you can see that anything that consumes storage is part of the layer creating instructions. Hence, whatever we discuss, the read-only layers are the only ones that modify the file system in any way. Let's go back to our diagrams now. And here this container has consumed 10 megabytes of space. What happens if this container dies? This 10 megabytes of data is lost, because we do not have a persistent storage with container 2, and containers are ephemeral. They come and go. Let's say if this container was just supposed to generate some data and then go, then how can we ensure that whatever data this container generated is saved somewhere? And here we have the concept of Docker volumes. The Docker volumes are there to ensure that data that you want persisted can persist. Let's move to the next section now. Docker storage. Docker handles storage via storage drivers and volume drivers. So whatever writable layers that we have been creating up until now, be it in Docker or be it in Kubernetes, what are we using? We are using the storage driver. As storage drivers handle the container's internal ephemeral data tied to the container's life cycle. So as soon as this container dies, this 4 MB of data is lost. And why is it lost? And who is playing a role in helping create this writable layers on top of these read-only layers? It is the storage driver that is helping us. Now think of them as file system for containers, manage container, internal storage, and file organization. Kubernetes follows the same. So Kubernetes has something called container runtime interface, CRI, that interacts with the storage driver. The examples of storage drivers are overlay FS. This is the most widely used and is also the default on Linux systems. Then there is ZFS. This one is an advanced one. Then you have AUFS. This is now legacy. The advanced version of AUFS is overlay, which is now being used. Then you have ButterFS. This is for large scale environments. If I want to verify which storage driver I am using, I can go to the terminal and I can simply run docker info. This will dump me all the information about my Docker deployment. If I move above, I see here storage driver and we are using overlay 2. And if I go back to my diagram here, we have volume drivers. So when do volume drivers come into picture? Whenever you attach external storage to your containers, volume drivers are active. They handle external persistent data that exists independently of the container's lifecycle. So even if this container dies, my data stays here. So for example, if you have a laptop and you have connected an external HDD to your laptop, and if your laptop crashes, God forbid, I hope that never happens, but your data is still safe in your hard disk. Similarly, if this container dies, any volumes that I have mapped to this container externally will stay. That data inside that volume will remain. Think of them as external hard drives for containers. Manage persistent data storage that exists outside containers. Now, when I talk about Kubernetes, here we have volume drivers. Kubernetes has something called CSI plugins, container storage interface plugins. They help Kubernetes to map volumes from different cloud providers or from different sources. So we'll discuss the Kubernetes CSI plugins in the next lecture. For now, the examples of volume drivers that are used by Docker are: first is local. This is the default driver, and in the demo we'll see the local driver is being used. And different cloud providers like AWS, Azure, GCP, they will have their own drivers which can be used to mount storage from their cloud onto our Docker containers. I hope this makes sense. Now, if you are thinking, if volume drivers exist, I don't need storage drivers, but that is not the case, because your containers will still use ephemeral data, will still have data that you do not want to persist. Hence, both of these work in conjunction when you are dealing with a production grade Docker deployment. Let's move down now. Docker installation. So first, let's look at this. Docker installation options. First is Docker Engine, second is Docker Desktop. Docker Engine is only available for Linux. Why is this? If you look at it architecturally, Docker Engine is only designed for systems that have Linux kernel. Does macOS have a Linux kernel? Does Windows have a Linux kernel? They don't. Hence, Docker Engine cannot be directly installed onto macOS or Windows, but it can be directly installed onto any Linux distribution. That's because they all have Linux kernel as the base. Hence, Docker Engine runs natively onto them. But why does Docker Engine have this dependency on the Linux kernel? Because Docker Engine relies on certain features that Linux kernel has to offer, and these features are control groups, network namespaces, and many more. Second installation option is Docker Desktop. This is what we have been using. If you look at the top here, I have a Docker Desktop. If I go to the dashboard of that, you will see all the containers that are running. You can also see images, volumes that exist in my Docker Desktop installation. Let's get back here. When I install Docker Desktop encompasses a few things. It has a Docker engine. Yes, it does have a Docker engine. That's why we are able to run containers. Then it also has a Docker Compose. It has a GUI dashboard, which we just saw. But Varun, how is Docker Desktop able to achieve that? It is able to achieve that because whenever you install Docker Desktop onto Mac OS or Windows, there is a lightweight Linux virtual machine created, and onto that virtual machine, the Docker engine is installed. So all of you who have installed Docker Desktop, there is a small VM created, and if you're using Mac OS, then the Docker Desktop is able to create that VM because we have Apple virtualization framework and Windows has WSL2, which is Windows subsystem for Linux. I hope this clarifies things. And Docker engine, again, it consists of, we saw that in day one, Docker engine consists of the Docker CLI, REST API, and the Docker daemon. Hence, Docker engine is of paramount importance. Now this is clear. Let's move to the next section. Next section is the demo. So let's go here. I'll clear my screen. I will run a command docker volume create my vol. As simple as this. I'm creating a volume. I'll press enter. My volume is created. Now I will run docker volume inspect my vol. I'll press enter and you see a volume is created, and this volume uses the local driver. This is exactly what we saw in the diagram. This one local is the default driver. Let's go here now. I will now map this volume onto a container. So let's write docker run -d. Name of the container will be my container one. -d is added so that this container runs in the background. Then I'll write -v as in -volume. Then I will say that whatever volume I have just created, my vol, just map that volume onto the app directory of my container. And you know, if I go back here, app is my working directory. This is where all the action is happening. This is where we have copied our app.py, and app.py is the logic of my application. If you want to deeply understand that, you can go watch day 3, but at this time you do not have to understand what this image will be doing for us. A running instance of this image will be doing for us. Hence, let's just concentrate on volumes for now. I go here and then I will tell this which image to use, and it will use the image that we just created, my -image. I will press enter, but before I do that, you see that the format is -v. First you mention the volume that exists on this host, on this Docker host on my Mac machine. But is it my Mac machine? We'll answer that question in a little while. And then we are saying that this is where you want to map this onto a container. And this format is similar. Docker uses this format for ports as well, for port forwarding. So if I go here and go to day 3, you see we use this command docker run -d -p was for port forwarding. So we were saying here anything that comes onto port 8080 of the host should be forwarded to container port 80. First the host port and then the container port. And here as well, we are first writing the name of the volume that exists in the host, and then we are saying /app, which is on the container. Let's press enter now. It says that the container has been created. Now let's exec into the container. I'll use docker exec -it my container 1, and what I want to use is the born again shell bash. I'll press enter and you see that I'm directly taken to /app directory. And why is that? Because this becomes the working directory for my container. So whoever copies something or whoever logs in into this container, by default they will be taken to this directory. So let's run ls here, and we, as expected, we see app.py here. What I'll do is I'll create another file and I will write in this file, this is my delta data, delta as in the writable layer that I'm creating. And then I will write here, redirect this data into file.txt. I'll press enter, I'll hit ls, I see that file exists, I'll cat on this file and I see this is my delta data. Now I will exit out of this container. What I will now do is I will delete this container, docker rm, I'll add a hyphen flag because that container is running and I'm deleting a running container, which is why I'll have to force delete it. I'll write my container 1, I'll press enter now. It says my container 1 deleted. The container is gone. Now what happens by default is whatever you see here, my hyphen vol, this volume gets created in a folder called var lib docker, and inside that there is a volumes directory, and inside that these volumes get stored. They take the storage of your host. So let's do one thing, let's cd into this. No such file or directory. Why is it? If I were on a Linux machine, then this would have worked, but I am in a Mac machine, and as I said, we have installed Docker Desktop, and behind the scenes Docker Engine is configured onto a small Linux VM, but I am trying to access this file from my Mac machine directly. That will not work. So what I'll have to do is I'll have to log into my small Linux VM that Docker Desktop created in my macOS and then access this path. Or I can create another container, map the same volume on that container and check if my data exists or not. So let's go with the second option. I will run docker run -it -rm states that remove this container once the command is done, and our command will be accessing the shell. And -it is for integrated terminal, and then I will write -v. The volume name that I want to mount is my vol, and where I want to mount it in this container, I want to mount it onto /app. I'm not naming this container here, and I'm asking this container to use the alpine image, and then sh for shell. I'll press enter and I'm inside the container. If I run ls, I see that the first directory is my app directory. If I cd into the app directory and hit ls, file.txt exists here as well. This is because this is a volume that we created. Now any container who has this volume can store the persistent data onto this volume, and even then if that container goes away, our data will stay safe. If I cat into this file, you can see that this is my delta data. This is what we echoed into this file. Now I can exit this container and the container is gone. If I run docker ps, I do not have any running containers that we just created. These three are part of my Kubernetes in Docker, that is kind installation. These are running my Kubernetes workloads. One is the control plane and two of them are acting as my worker nodes. Okay, so what I will do is I'll clear my screen now and let me think if I have anything else to tell you. Yes, let's discuss. I'll go to my GitHub notes, and please visit these notes, and I would be very thankful if you can star this repository as well. Now I'll click on types of Docker volumes. What we have discussed, the volume that we created and then mounted, these are called named volumes. One thing I want to add here is we first created the volume and then mapped the volume. We first used docker volume create, and then once the volume was created, we mapped it. However, we could have directly run this command, and this command behind the scenes would have created the volume for us. Okay, so named volume is something that we just used. This is the default Docker managed volume, and if you are using Docker volumes in production, then you would be using the named volume. Second one is bind mount. This one mounts a specific host directory to the container. Now, if you are mapping a host directory, then your container should have appropriate permissions onto that directory. Then only writes or reads or executions will happen, because if you see cons is tied to the host path, can cause permission issues. Then there is tempfs. Tempfs is the volume that is mapped from your memory itself, from your RAM. So hence the performance will be very fast. However, if your container reboots, your data is gone. If your host reboot, then obviously your container will be down and also the data will be lost. So use this with caution. Majorly you will be using named volumes. Okay, that's all I wanted to talk in this lesson. Thank you for watching. I hope you now understand Docker volumes. In the next lecture, we'll be discussing Kubernetes volumes. If you have any questions, feel free to ask them in the comment section and I will reply. If this helped, do consider liking, sharing and subscribing. It will mean a lot to me. Thank you very much.